Exponential functions are functions of the form b to the x power, where b is the base of that exponential function. A common base that we can see with exponential functions is a base of e, which is a specific mathematical value, a specifically defined constant, and it's based around this expression 1 plus 1 over n to the nth power, an expression that pops up in a lot of different scenarios in math, particularly in finance formulas, investing formulas. What we want to do is take a look at what happens to the value of this function as we plug in different values. For instance, if we started off with a value of n equals 2, then this expression would be equal to 1 plus 1 over 2 squared, which would give us 3 halves squared, or 9/4, which is 2.25. Then what we want to do is plug in increasingly larger numbers. So we'll jump ahead to n equals 200. We would evaluate this in the same way, and what we would get would be approximately 2.711517, and then we'd have repeating decimals after that. If we jumped up even higher and plugged in a value for n of 2000, we would get 2.717602, and on, another repeating decimal. And what can actually be shown or proven mathematically is that as n approaches infinity, meaning as we continue plugging in larger and larger values for n, this particular expression is going to approach a specific value, 2.71828, and on and on and on. It's a repeating decimal, but it is a precise specific value that we refer to as e. What's important to keep in mind then is that anytime we see the letter e, is that this is not a variable, but a number. A very fixed, specific number, in the same way that pi, which you've probably used in some previous courses, we say is approximately equal to 3.14. There's an exact value that's a infinitely repeating decimal. The value e is approximately equal to 2.72, but really it's this infinitely repeating decimal value. Whenever we see that value for e, though, we just need to tell ourselves, remind ourselves that that's not a variable, that is a fixed numerical value. All exponential functions have two components: a growth rate and an initial value. If we again consider an exponential function, f of x equals b to the x, but we add in a couple of additional constants, a, which is being multiplied by that exponential expression, and a value c, which is being multiplied by the exponent that b is being raised to, then what we've introduced is the initial value a, and the growth rate c. That means that anytime we have an exponential function, just looking at the function, we can determine its growth rate by looking at that value for c and the function's initial value, so the value of the function when x is equal to 0, just by looking at that value for a. If we had a base e exponential function, we could still introduce those same two constants, but change our base. Now what we have, because this is a base e exponential expression, that growth rate is referred to as a continuous growth rate. But the idea applies. That value for c is telling us how quickly our function value is increasing. meaning we can compare the growth rate of two functions or tell which function is increasing faster by just looking at those values for c and comparing those two numbers. It's also important to note that anytime our value for c is positive, or I should say greater than 0, then what we have is exponential growth. That function is increasing like we saw in the curves that we looked at above. And if that value for c is less than 0, then what we would have is exponential decay. So rather than our graph curving up to larger and larger values as x increases, we would see a flipped version of that graph above, where as x gets larger and larger, our function value is headed to 0. And again, we can determine that by looking at our value for c, and we can determine which function is growing at a faster rate by comparing those values as well.